Welcome to this video lesson. In this video, we will be looking at tangents and their significance in physics. The central idea of tangents is that those are a line, it's a straight line that touches a curve only at one point. And this line can be used to find instantaneous rate of change, which is a huge concept in physics. So the learning goal for this particular video is to be able to draw tangents to a curve, calculate slope between 2 points, and to estimate the slope of a tangent. So I'm going to bring this up and let's talk about tangent again. So again, tangent line to a curve at a given point is a straight line that touches the curve at that point. This is kind of like the mathematical explanation of it. For me to understand it, I think of it differently. So whenever you have a curve, we can kind of have one line that would, one straight line that can represent the slope at that particular line. So for example, if you look at this line, it's going up, and as it's going up, the slope of this line, if it was to be represented by one straight line, would be pretty high. The slope value would be pretty steep. And as the line goes down, the steepness starts to get lower and lower. And at this top here, the steepness of the line isn't that much, meaning the slope isn't that high. And then as we go down this way, the slope is going to start to increase again, but in the negative direction. So it's getting steeper. The slope isn't getting smaller, it's definitely getting bigger in terms of value, but it starts to become negative because it's going in the opposite direction. So mathematically, the way we think about it is if we have a straight line, if we have a point very far away from it, the slope is like this. As we move this point closer and closer to this point, the slope starts to really represent the slope at this point. So you can see that this slope is closer to the tangent, and then we move this point closer, it starts to represent the steepness of this portion of the curve a lot better. And as we move this closer, and if we connect those points, we get that tangent line. So if the spacing between the two dots is approaching 0, then we can represent that tangent line a lot better. So we got an image that I took online here, and we can see how the slope of the line is shown in different locations. So I'm going to actually zoom into here, and you can see that the steepness right here of the line is represented by this. So I'm going to actually use purple to kind of highlight these. You can kind of see how well that line is representing the steepness at that point. So this line over here represents the steepness here. And you can kind of see the steepness here is pretty high. The steepness gets lower around here. The steepness here starts to increase again, but in a negative direction. So this one is going in this direction. Just need to change it to this tool. And then at this point, for example, the steepness is like this straight line here will represent the slope. Let's do a few more on this apple. We have this point over here. If we were to draw one straight line that represents the slope or the steepness, you can see that it's super steep here. Steepness reduces a little bit and the steepness just gets less and less. So we're going to draw a tangent right here. It's going to be approximately like this. If you don't have a tool and if you're just sketching the tangent, it's not going to be perfect, and that's okay. If you ever need to estimate a value based on the tangent, it'll be an estimate question, and there will be a range of answers because if you're just doing it by hand, it's very difficult to get a perfect answer. Good. So again, this steepness here, steepness here, steepness here. At sharp points, we don't talk about steepness. We're just going to do it over the curves. And if you have a straight line, actually, if you have a, let's say your curve starts this way, goes curves and then goes straight from here. So the slope here, pretty steep. Steepness gets less, steepness gets less, and the steepness here doesn't change. The steepness here is always, if it's a straight line, the steepness of the line is that steepness of the straight line. So the tangent and the straight line are the same when we have a straight line. Okay, so once we're done this, let's draw a few tangents to a circle. I highly recommend that you just draw a circle and just draw a few tangents to it at different locations. It doesn't have to be these exact locations. But you can see that at point D, if I want one straight line to represent the steepness, something like this. At point C, that's the top of the triangle, sorry, top of the circle. You can see that at top here is approximately flat. It's a flat line, so the slope there or the steepness is 0. Steepness here goes kind of like this, so that's kind of like a negative slope, but it's pretty steep. It's just negative. And at point A, it's kind of in this direction. At point E, it's going like this, and at point F, this is a straight line, so the tangent at a straight line is just represented by that straight line segment. So in this question, we're asked to draw the tangent of the following curve and state qualitatively whether the slope is big, small, or small, and whether it's positive or negative. So slope here is pretty steep. Oh, actually, let's start with A. Over here, the slope, you can see it's pretty small, I would say. So I'm going to say small or low, or yeah, small is good. Is it negative or positive? Well, when we're looking at slopes, if as we're moving to the right, if the line is going up, it's positive. If we're moving to the right and it's going down, it's negative. So this is positive. For B, we can see that if you were to stand on a slope like this, if it was a snow or ice, this would be a challenging time. This is pretty steep, so I'm going to say the slope is very large here, actually. And is it positive or negative? Well, as we move to the right, it's going down. That means it's a negative slope. For part C, it's pretty flat, so I'm going to say actually this is the steepness high or low. In this case, the steepness is 0 steepness. And when it's 0, there's no negative or positive, because as we move to the right, we're not going up or down, so it's not positive or negative. Point D, we can see right here, as we move to the right, it's going down. That means it's negative, and it's super steep. This is very, very steep, so it has a large value, and it is a negative as well. Point E, we can see that it's a pretty small, sorry, yeah, the steepness isn't that much, so I'm going to say it's a small value in terms of slope. And it's also negative because as we move to the right, we're moving down. This one, steeper than this, not as steep as this. I'm going to say this is approximately medium. Again, these are kind of like an approximation. It's not perfect. This is also negative. It seems like I only had one positive slope, which is fine. Good. And that's how we do these type of questions, and that's how we kind of estimate the steepness and and state the sign of a tangent. So let's move up to the next section. So the next thing we're going to look at is some terminologies, some that are used so often in physics that we need to be really good at them. So the terminology rate means the ratio between two quantities. The most common, so ratio means something over something else. The most common type of rate that's used in physics is per unit time. So that would mean that is one quantity over time. So the denominator in terms of the ratio is always time. Remember, per means divided by in terms of how we translate that into math. So per has to do with division. So we have a certain quantity on the numerator, and we're going to divide that by unit of time in the denominator. In terms of terminology, the slope of a line between 2 points. So if we're taking a slope between two particular points, then what that represents is the average rate of change. So in terms of terminology, if we have 2 points, then we're getting the average rate of change, and this is slope between 2 points, between. But if we have, whereas the slope of tangent at a point, so a tangent is always represents the steepness and the sign of the slope at one particular point, so it can't be between 2 points. So slope of a tangent at a point shows what we call instantaneous rate of change, and I need you folks to really get your head around that and kind of understand that. We're going to talk about the usage a lot more later, but for now I need you to understand the difference. So slope between 2 points is the average rate, but slope at a point, and this is done by the tangent, are finding the slope of a tangent, represents the instantaneous rate of change. So how does that look like in a graph? So if you have 2 points, for example, let's say we have this point in time and this point in time. So we start at time of 0 seconds and we go to 20 second over here. So if I were to draw a line between these two and find the slope between those 2 points, that is going to show the average rate. So on average, what is the rate of change here? So actually, let's draw that out and I will change it a little bit later. But let's say we have this line. So if you look, the slope here is very high, very high, very high. So very high values here, and they're all positive. Here is 0, 0, 0. And these ones are negative and they're medium. So when you kind of average the slope in this region and this region and this region over this time, the average, this one was very high, 0. This was low, negative. So when you add them up, you're going to get something which is still positive. It's still steepness, mainly coming from this part, but not as steep as this one because you had some steepness of 0 here and some negative steepness, which will, on average, take the slope down a little bit. So that's why the slope between 2 points is the average, it's not the whole thing. Or it's not an instantaneous time. But if you want the slope at an instantaneous location, let's say somewhere at 30 seconds, for example, if you want the slope right at that point, what you have to do is you have to draw a tangent, and in a straight line, the tangent and the straight line have the same slope, and kind of find the slope at that point. And this represents the slope instantaneous rate of change. So how is the y value or the vertical value is changing with respect to the horizontal value, in this particular case being time. Let's do a few examples. So we're going to start off with this one. I'm just going to erase everything that I had prior so we can work on this example. Calculate the average rate of change of position between times 0 and 10 seconds and 10 to 15 seconds. Okay, so the question says to calculate. Calculate is a key term or a key command term used to signify that you have to show your work as you're doing the calculation, and you have to show the final answer. So we'll have to do that. So in this case, calculate the average rate. So average refers to having 2 points, and average rate of change of position. So we're trying to figure out what is the average rate of change of position. Position is given to us in the y direction here between time 0 to 10 seconds and 10 to 15 seconds. So because the most common terminology when we're talking about rate of change in physics is rate of change per unit time, we haven't mentioned it here. So another way of wording this would be average rate of change of position per unit time between these two. So what is the ratio of the change in position over change in time? And that's represented by the slope. So between 2 points, times 0 and 10, we want to figure out what is the rate of change. We have to find the slope between these 2 points. The slope is the change in y over change in x, or rise over run is another way of looking at it. So between 0 to 10 seconds, we will take the average rate of change will equal to the slope. So the slope at that point is going to equal to rise over run. So rise over run. So that's how much the y value or the vertical value has changed over the change in the x direction. For the y direction, from here to here, we've gone up by 60, positive 60, because we're going up, and the x value has changed by 10, because we've gone by 10. So this is going to equal to 60 divided by 10. And in terms of unit, and we'll do the unit in a second, 60 divided by 10 is just 6. And in terms of units, the position, the change in y had a unit of meters, so that's going to go on top. And the change in x had a unit of seconds. That's the one in this direction. That unit was seconds. So I'm going to put seconds. And you can also include this as 6 meters per second in this format as well. What was the change in position between time 10 to 15 seconds? So for 10 to 15 seconds, it's the same idea. So the slope between 2 points will represent the average rate of change between those times. So at 10 seconds, we were here. At 15 seconds, we are here. So we can see that the slope is going to be rise over run, or change in y over change in x. We can see from here to here that y isn't changing, so the change in y is 0. The change in x from that time to that time is basically 15 minus 10. So I'll actually write it down, 15 minus 10. And when we do this, we will get 0. So the slope is 0, so the rate in change of position is 0, meaning that the position over this time wasn't changed. Does that make sense? Well, this person or this object was at 60 meters at 10 seconds, and they didn't move, their position was still 60 at time 15 seconds. So the rate of change was 0. They just didn't move over time. And this is kind of what that means. Let's move on to another example here. So in this case, calculate the average rate of change of position between time 15 and 40 and 40 and 55. So we're given 2 points. in both cases, so that's going to calculate the average rate of change and not the instantaneous. For the first one, between 15 and 40, so 15 is here, 40 is here, so between 15 and 40 seconds, the average rate of change is basically the slope between those 2 points. So it's going to equal to rise over run. It's going to equal to my rise, which is delta y, and run, which is delta x. So for delta y, we can see that we start from here, we go down. And we go down, we're going negative and not positive. So we go down by 20, 40, 60, 80, and 100. So the change in y from here to here is negative 100. And the change in x, 5, 10, 15, 20, 25. So we can also think about it this way. So the change in x is we have 40 seconds at the end, and we start with 15. So actually, I'll write it out here. So 40 minus 15. And here, from here to here, our final value is negative 40 meters for our position. And our initial one here, I was at a y value of 60. So I will do that. Again, you can do it using math by subtracting, but if it's easy enough, you can just count. That's negative 20, 40, 60, 80, 100, and that's same as negative 40 minus minus 60, and that's negative 100. And 40 minus 15 is 25. And when we do that calculation, we will get negative 4. And my units for y is meters, and I'm dividing that by seconds, so that's going to be my units, or negative 4 meters second to the negative 1. So both ways are acceptable. Finally, for the last one, it says rate of change for 40 to 55 seconds. You can pause the video and try this on your own and then check your answer. I'm going to go ahead and do this. It's going to be the same idea here, and then it's going to be equal to rise over run. That's delta y over delta x. So delta y from 40 to 40 is here. So the rise is going up. My final value is 0, and my initial one is negative 40. So I go up by 40, pretty much. I can write that out here. And we go to the right by 5, 10, 15. You can either just, we know it's 15. Mathematically, you can write the very last time, which is 55, and subtract it by the second one, which is 40. And this can simplify to 8 over 3 meters per second, or you can also change this to decimals. Let's assume that everything had 2 significant figures. I will specify, if we have a test situation, what the accuracy is. So this is going to be approximately 2.7, and meters per second can be denoted this way as well. Okay, let's do a few other examples, and then this one, draw a tangent to curve at time 2 seconds. So we're gonna do that first, and then hence estimate the rate of change of position at 2 seconds. So let's talk about terminologies here. So it says draw. I'm going to change that to a sketch, actually, because it's very difficult to draw things very effectively here. We're just going to do our best. And then so sketch the tangent first, and then it says hence. Whenever we use the terminology hence, it means you have to use the information from previous parts of the question, part or parts of the question to answer this. So we need to use information from the part A, and we want to estimate the rate of change. So estimate means that because you're not going to be doing things perfectly and you don't have perfect numbers here, your final answer will be in a range of different values. So it won't be one exact value. Let's try to go for a tangent here. I'm gonna draw it like this, and I think this is actually quite good. I kind of like it. So I'm gonna actually go all the way, extend my line all the way, so you can see that it starts. And if you have a ruler, well, actually, do use a ruler whenever you're doing this. You can see that the curve kind of starts with a low slope. The slope just keeps increasing, and I think this is a decent tangent, which kind of shows what the slope is in that region, and then just gonna get steeper and steeper up here, and that's at exactly 2 seconds. So now that we've done this, we're going to estimate the rate of change of position at 2 seconds. So rate of change is the slope. So we're going to find what the slope of this is. I'm going to choose 2 points on the line. So I'm going to choose maybe this point over here. And again, we are doing an estimation. So this is approximately here and here. And we're going to use one other point. I'm just going to use this point over here. Easy enough. So this point over here has an x value of, or time value of 0, and displacement. Oh, this should be called position. I probably took this out of the internet. I usually don't make that mistake. So this is 0 and 4. And this point over here is approximately, well, it's for sure 4 seconds. And the y value is approximately 15. So I'm going to leave it as 15 here. So to find the rate of change, and in this case, we're doing the instantaneous rate of change because it's at one particular point. We are going to take the slope. So this is going to equal to delta y over delta x. The change in y, our final y value is 15. So that's this one over here. And then our initial one is 4. So we're going to do 15 minus 4. And we're going to divide that by the change in x. So my final x value is 4. Our initial one here is 0. So I have 4 minus 0. So that's going to be 11 divided by 4. And assuming, let's add to the question, assume 2 significant figure accuracy. And if that's the case, we will get approximately 2.75, which is rounded to 2.8. And we got meters for our delta y, and we got seconds for our delta x. So we can also represent this in this format. And that is the rate of change of position at 2 seconds. Okay, let's look at the next thing over here. So I'm going to shift this up. And okay, very similar question. Draw the tangent to the curve at 3.5 seconds. So try this out on your own if you can. And I will do it as well, and we can kind of see the difference between our answers. So at 3.5, it's somewhere here. The slope here is pretty steep. You can see that the slope here is kind of like low. It just starts to get higher and higher and higher and higher and higher and higher and higher down there. So I'm going to draw this as I'm just trying to do a good job here. Okay, I'm pretty proud of myself. I think this line is a very good representation of the slope here. Again, kind of changing like this, and then it's kind of steepness is kind of like that here. So in order to find the slope of this line, I'm going to choose two random points on the line. I will do my best to choose my points that are far away from the line. So I'm not going to sorry, far away from each other. So I'm not going to pick 2 points that are too close to each other. That's not going to help. So one of the points I can use this point because I know based on a definition of tangent, this line will be touching at this point. So this point has an x value of 3.5 and a y value of 17.5, and I'm saying 17.5 because this is 15, this is 20, and this is halfway. So another point on the graph that's a good one and not too close. This is a decent one, but it's too close. I just have to estimate what that point over there is. That will be another good point. So point here. And this point over here in terms of x, this is 1.5. That's kind of 2, so I'm going to estimate it as 1.8-ish. And for the y value, it's 0. The y value, that's why I chose it actually, because the y value is just 0. So that's nice. Okay, so now let's find my slope value. So sorry, my rate of change. So this is part A. Sorry, I forgot to mention a few things. So this question again, I'm going to change this to sketch because it's not going to be perfect. In terms of the what you need to represent in your work, in terms of your sketch, this line needs to for sure touch the curve at 3.5 seconds, and its slope should also represent the slope of the line. So if you were to be marked on this, it would be approximately 2 marks, sometimes 3, depending on if I'm looking for more information. So yeah, so that would be a sketch, and then hence we have to use this information, which is this line, to estimate the rate of change or instantaneous rate of change. And so instantaneous rate of change is the slope. So maybe you might get a mark for understanding that. The slope is equal to rise over run. The change in y, I'm going to have this as my starting position, this is my end position. The change in y, last one is 17.5, initial one is 0. And for my x values, it kind of, my last one is here, my initial one is here, so that's 3.5 minus 1.8. I'm going to add to the question, assume two significant figure accuracy. So once we get the slope on this one will be approximately 10.294 dot dot dot. I need this in two significant figures. So if I were to write it as 10, that's just one significant figure, but we are asked for two in this case, so I would have to express this as a scientific notation. So I'm not going to write it like this. I'm going to write it as 1.0 because that has two significant figures times 10 to the 1, and that represents the value in two significant figures, and that's equal to 10. 1 times 10 is just 10, and my unit is meters per second, and you can write that or meters per second like this, completely up to you. So basically, based on my based on my tangent, which again I'm pretty proud of, my final answer was approximately 10 meters per second. I think with a question like this, again, it depends on the situation, but since it's an estimate type questions, when you were drawing yours, maybe yours was a little bit off, maybe it was a little bit this way, maybe it was a little bit steeper. So I will accept a range of answer here, probably somewhere between 8 to 12 meters per second, but I won't be accepting answers like 25 or 1. So the slope needs to be pretty representative, but I will accept a range of answer because everybody might be a little bit off, or I don't even have the perfect answer, but the range of answer, because it's an estimation and it's a sketch question, not everybody will have the same exact tangent here. Okay, let's do the very last part of this. Draw or sketch. We're going to use the same terminologies. We're going to use sketch and at 6 seconds. So I'm going to go at 6 seconds. Here we got a straight line. Whenever we have a straight line, the tangent is going to follow the exact same line as the straight line, because the curve at this point has that exact same slope. And we're going to follow the same steps. Estimate the rate of change, or the instantaneous, I should call it instantaneous rate of change, is determined by the slope at that point. I'm going to choose 2 points. I can choose this point over here where it's actually touching. So that has a x value of 6 and a y value of 17.5. And let's choose another point. I like this one. This one is also right at the point, so this one has an x value of 4 and a y value of 25. And okay, we already know the slope is negative because it's going in this direction. So as we move to the right, it goes down. And we can easily just find x and y by subtracting things. So here, slope is going to equal to the change in y, change over change in x. Change in y, our final value is 17.5. Initial one is 25, so subtract those. And our x final one is 6 and initial one is 4. Once I do the calculation, assuming again, let's say 2 significant figure, then I will get an approximate value of negative 3.8, rounding it up, meters per second, or meters per second. Whenever you're calculating the slope, just make sure you go back to the diagram and make sure that if it's negative, your final answer was -2. If it's not, you made a boo-boo somewhere. And other than that, and so during this video lesson, we worked on a few things. One was drawing tangents, and a tangent represents the slope of a line at a particular point on a curve, and it helps us figure out what is the instantaneous rate of change at that point in physics. So the other thing you need to know is that if you were to find the slope between 2 points, it will show you the average rate of change. So let's talk about this quickly again. So if I were to find the slope from here to here, that's on average the rate of change in all of these ones will add up to this slope. So this slope over here, you can see has a medium steepness and is positive. And if I take the instantaneous slopes here, they're very little. They start to increase. They start to really increase as we go this way. So here the slope is small, and here the slopes are very large. So if you were to average all of these ones, very large values and values close to 0, you will get something in between. And this average slope over here is pretty much that average. High values plus small values, all divided over the time period will give you that average. So I hope this video was helpful. And I hope that it can assist you with your future physics journey.